Hi, everyone. It's really a pleasure to be here. About a month away from launch, it goes without saying that it is with great excitement that we'll be sharing some of the science that I will be doing with the James Webb Space Telescope in Cycle 1. And that has to do with PAHs in low metallicity galaxies. And of course, I know probably many of you are not familiar with PAHs are, and so not to worry, I will explain all about it. So PAH stands for polycyclic aromatic hydrocarbon, and PAHs are large molecules that are that have aromatic components to them. An aromatic component is just a ring of closed electrons. And these molecules are composed exclusively of carbon and hydrogen. You can see examples in the schematic here on the left, going from just a small molecule to a cluster of molecules to nano-sized particles, which are basically comparable in size to very small dust grains. And so those molecules are really like the bridge between the molecular ISM and the interstellar dust that compose a lot of the galaxies that we can observe both in the nearby universe and in the high redshift universe. And to build your intuition on those molecules, here on the right is an image of a PAH molecule taken with an atomic force microscope. So what does this have to do with astronomy, you may ask? Well, it turns out that the interstellar medium, which is all the fluff of dust and gas between stars and galaxies, all this interstellar medium, or ISM, is full of PAHs. And those PAH molecules shine brightly in the near-infrared and mid-infrared, which is the wavelength range that James Webb will be so good at observing. And so all these PAH molecules need to shine is to be excited by photons in the far ultraviolet that are emitted by young massive stars. And so that means that basically PAHs shine brightly in star-forming regions. And you can see this on two images of star-forming regions in the Milky Way. On the left is the Caspar Nebula, and on the right is Orion. So on the left here, the PAH emission is observed with Spitzer at 8 microns and is shown in green. And on the right, also with Spitzer at 8 microns, the PAH emission is shown in red. On the left here, what you can see in red is the hot dust that is heated by those young massive stars, very blue stars. And stellar light is shown in blue in this image. And so you can see those PAHs tend to surround the bubbles of hot dust and even ionized gas that is blown away by those powerful massive stars. So the ISM is full of PAHs, and as a result, entire galaxies also shine brightly in PAH emission. Here's an example on the left, which is M82. In the optical or visible wavelength regime, it looks pretty ordinary. It's a cigar-shaped galaxy. And it only is when you look at it in 8-micron PAH emission that it turns out to be a smoking hot cigar. Where the PAHs are ejected from that galaxy, either by the powerful winds of massive stars or some kind of AGN activity. But in any case, you can see those super winds in PAH emission at 8 microns with Spitzer, and it's quite impressive. And on the right here, you have a less extreme case, which is a very Milky Way-like galaxy. Seen again at 8 micron emission in red, so showing the PAHs. The ionized gas is in green and the stars are in blue. And so what you will immediately see is that the entire spiral structure of that galaxy can be very easily observed in the PAH emission. And so PAHs are a very useful tracer of ISM and galaxies in general. And specifically, they have several emission features in the near-infrared and mid-infrared, so between roughly 3 microns and 13 microns. You can see an example of PAH spectra observed with Spitzer here on the left. You can see the features at 3 microns, 6 microns, 8 microns, and 12 microns roughly. Those are the top and bottom are just two different regions, NGC 7027 and Orion at the bottom. And so those PAH features are created by different modes. So for example, you have the carbon-carbon stretch here. So that is the molecule that has two carbon atoms tied together with an electron bond, and they can stretch. And that creates a feature. Similarly, you can have a carbon-oxygen in-plane bending, out-of-plane bending, and another carbon-hydrogen stretch here at 3 microns. And so what that means is that the shape and location of the different features should trace the properties of those molecules. And this is illustrated on the right, where you can see at the top the spectrum of a neutral PAH, so not charged. And at the bottom is the spectrum of an ionized PAH. So this one is charged. And you can see the shape of the two spectra are quite distinctly different. And that's great news for us astronomers because it means that we can observe those spectra and use the shape to infer the properties of those molecules that are so fundamental to chemical evolution in galaxies. So coming back to this example of M82, of course, on the left here, you can still see the emission from PAHs at 8 microns in red. So this is the hot wind that's blown out of the galaxy. But Spitzer also actually took spectra at different regions of these superwind. And so on the right here, you can see the corresponding spectra going from short to long wavelength from left to right, and 3 regions, the north, the center, and the south from top to bottom. And you can see that the shape of the spectra changes significantly from one region to the next, indicating that the properties of the superwind also change. And we can use those spectra, the shape of those spectra, to actually infer the properties of the gas and dust in those in this hot superwind. So why do we care? Why is this important? Well, the PAHs are everywhere in the ISM, and they also tend to be excited by young massive stars, blue stars. And so that makes them a really good tracer of star formation, not just in the nearby universe, but at all redshifts. And so on the right here, you can see a plot of the rate of star formation in a sample of galaxies that contains about 100 galaxies at low redshift, so between basically redshift 0 and 0.4. And on the y-axis, you have the star formation rate inferred from PAH emission from Spitzer. And on the x-axis, you have the rate of star formation inferred for more classical tracers, which are ionized gas that we trace with H-alpha. And indeed, young massive stars actually ionize their surroundings, and so ionized gas traces those massive stars. And then also hot dust traced by the 24 micron emission in Spitzer. And that really traces star formation that is still embedded in the native dust cloud. So you sum the two, you get the total star formation. And what you can see is that the two tracers, PAHs and H-alpha plus hot dust, correlate really well. And that basically demonstrates the power of PAHs in tracing the rate of star formation for the universe as a function of redshift. And it turns out that James Webb, because it is an infrared telescope, can measure those star formation rates in the high redshift universe. And so, for example, at the redshift of 2, when the universe was 3 billion years old, so 10 billion years ago, it can measure star formation rates as low as 10 solar masses per year in this distant universe. So it's very important that we understand the properties of the PAH molecules so we can actually use them to understand how those galaxies form stars in the high redshift universe. And of course, at redshift 2, so when the universe was 3 billion years old, there were much fewer generations of stars that had gotten a chance to enrich their host galaxies. And therefore, the metallicity of the universe back then was much lower than it is today. So the metal content of galaxies, on average, was about 1/10 of what it is today. Meanwhile, we have recently discovered, thanks to Spitzer, that there is a deficit of PAHs and PAH emission in those low metallicity galaxies. You can see this on the plot here, which shows the abundance of PAHs relative to the big grains, which is the regular interstellar dust that shines in the far infrared, and as a function of metal content in those galaxies. And in the high metallicity, sort of Milky Way-like galaxies that are on the right cloud of points here, the power abundance, is roughly like 4%. But in contrast, in the low metallicity galaxies, so those galaxies that are, 1/10 or 1 to 1% solar, there is a strong deficit of those power molecule and the corresponding emission. And we don't really know why. Coincidentally, this metallicity of about 1/10 solar also corresponds to the metallicity at which we observe the abundance of interstellar dust to drop dramatically. So above that above 10% solar metallicity, galaxies pretty much look like the Milky Way. They have a lot of dust in them in star-forming regions, but below this metallicity, we can barely actually detect anything from the far infrared, say with Herschel or Spitzer. So it's possible that the drop in the power abundance that happens at the same metallicity as the drop in the dust abundance is caused by the destruction of those power molecules by a very intense and harsh radiation field created by young massive stars due to the lack of shielding, right? Interstellar dust can shield interstellar clouds and PAHs from this very intense radiation and thus prevent their destruction. But in those low metallicity galaxies where there's very little dust, the radiation can travel through the interstellar clouds and destroy the power molecules. So that is one hypothesis. And the other hypothesis is that those low metallicity galaxies have a deficit of carbon. Carbon is, of course, needed to build those power molecules, which are composed of carbon and hydrogen exclusively. But it has been observed that the stellar carbon to oxygen ratio is much lower in those systems. And so it's possible that they just don't have enough carbon to build those molecules. So these are the two hypotheses that we have to explain the low abundance of PAHs at low metallicity, but we do not have the observations to tell which one is the correct one, or even both. And so what we're going to do is to observe two low metallicity galaxies with James Webb. We will take images, not spectroscopy. So those two galaxies are IC 1613. You can see an image of that one on the left, and Sextans A on the right. So IC 1613 has 15% solar metallicity, and Sextans A has even lower, it's about 8%. So we're really probing the very low metallicity nearby universe here. And we'll be using a suite of filters that can sample the near-infrared to mid-infrared emission from those galaxies. And we'll focus just on the dusty star-forming regions. The one in IC 1613 is highlighted here on the left, and the one in Sextans A is highlighted on the right. Those galaxies are sort of analogs to high redshift galaxies that had a much lower metal content. And therefore, they will be informing us on the properties of those PAH molecules in the nearby universe, which is the only place where they can be constrained in a resolved way, that is making maps of those properties, so that we can infer what's going on in the distant universe, where those galaxies are maybe not point sources, but close to it, and we cannot actually map those properties. And so we're trying to build a roadmap here from our local universe to the distant universe in terms of understanding those molecules. And so here's this plot again showing the abundance of those PAH molecules on the y-axis as a function of the metal content of galaxies. And this is where our two target galaxies fall. So IC 1613 at 15% solar metallicity, and about half of that for Sextans A, 8% solar metallicity. So we'll really be probing the metallicity regime that is of interest, where we have very low power abundance for a reason that we do not understand. So how we're going to do this? So we will be taking images with Webb of those star-forming regions in those two low metallicity galaxies in a bunch of filters that go from about 2 microns all the way to 15 microns. So this will be using NIRCam and MARY on James Webb. And so basically, James Webb was essentially designed in part to do exactly this. It has filters that straddle those PAH features, which you can see here in this model of PAH emission. And so, we'll be taking images in a bunch of those filters and hoping to map the properties of those PAHs. And I insist on the word map. We will not take single pointings. We'll actually taking images. So the spectrum here was made with models of PAH emission that were very recently released to the community. And of course, there will be some contamination by stellar emission, and we can account for that. And that's included in this model here. So we will be taking images in those filters, and then we will be modeling the brightness of the galaxies in each of those filters with PAH and stellar models to constrain the actually column density of those molecules, the mass of those molecules in each of those images. From the models, we have done simulations to make sure that we can actually infer the properties of the PAHs from those images, and specifically the fraction of ionized PAHs as opposed to neutral PAHs, the size distribution of those molecules, and also the age of the starburst, or basically burst in star formation, that is exciting the emission of those molecules. And basically, you can see in the plot here on the right that ratio of the images taken in different filters can directly trace those properties. So for example, here you have the ratio of the image in the F1130 wide filter to F770 wide filter as a function of the ratio of the F335M to F770W. So these are just ratios of images, right? And we color-coded those ratios based on the ionized fraction of the PAHs, low, standard, or high, the size distribution, so we're going from 3 to 5 angstrom average size, and then the age of the starburst, going from 10 million years to 1 gigayear. And so depending on the location of those image ratios in this parameter space, we can directly determine those properties. So this is a very powerful diagnostic method. Hubble will come in handy, though, to help with the determination of those properties for two reasons. The first one is that the JWST images that we'll be getting will constrain the mass of the PAHs along the line of sight. However, we are interested in the abundance of PAHs relative to the mass of the interstellar dust that exists in those star-forming regions. And so we will need to normalize this PAH mass to the dust mass. Typically, we trace the dust mass from far infrared emission, right? So interstellar dust is cold. It has a temperature of 20 Kelvin or so, 20 to 30 Kelvins. And so the peak of its emission is really in the far infrared between 100 and 200 microns. And we have images of those galaxies in 1 or 200 microns. You can see this on the right here. The Spitzer MIPS at 24 microns is in green, and the Herschel images at 160 microns are shown in red. So we have those images, but those are only at 35 arcsecond resolution. You can see it looks pretty blobby in this image. However, the JWST resolution that we're going to get for the PAHs is 1 arcsecond, so it's really not well matched to the type of observation that we're going to have. And so to get around this limitation, we will be using Hubble to map the dust in those galaxies. And so this is a joint Hubble and Webb program. We will be observing the exact same region with Hubble using filters that span the near UV to the optical, and of course to be complemented by the near infrared that will be observed with JWST. And so we'll be getting images that look like this on the right. This is actually an image of IC 1613. So the same galaxy we'll be targeting, but just not the same region. So this region is a stellar field. It has very little to no interstellar dust at all, and definitely no PAHs. But this is just to illustrate the kind of images that we can get out of Hubble. And using Hubble, we will measure the brightness of each of those stars in the near UV and optical, and we'll be able to infer how much dust sits in front of those stars. And that's what we need to do. And we can do this at very high resolution with Hubble, 1 arcsecond or so, which is very well matched to what JWST can do. So how are we going to do this? So we will have images in also several filters with Hubble. You can see the filters here that we'll be observing with Hubble in the top plot. So the near UV would be F275Y, for example. F475 is in the optical. And then I included the WIFC3, the Hubble WIFC3 in infrared filters, but in this case, we'll actually use, obviously, the JWST images in those filters. Now, we can use those images to infer how much dust is in those galaxies. You may know that more massive stars are bluer and brighter than lower mass stars, which are redder and fainter. But dust can also make a star look fainter and redder. And with just one band or one wavelength, we cannot disentangle the effects of stellar mass and intervening dust. However, if we have filters that go from the near UV to the optical to the near IR, we can disentangle these two effects. And that's shown in the bottom plot here. And there you can see the spectrum and the corresponding photometry for a very high, like a high mass star, say 10 solar masses, with a lot of dust in front of it. And that one's the blue spectrum. And then you have the spectrum of a lower mass star, which is 3 solar masses, with about half the dust in front of it. And you can see that the spectra, once you have the near infrared and optical and near UV, are well separated. The near infrared can constrain the stellar mass, while the near UV and optical will constrain how much dust is in front of those stars. And so using this method, we can actually get both the parameters of the stars and of the intervening interstellar dust that is reddening and making that star fainter. And so here's an example of this technique that we have applied to other galaxies that lie closer to us. And specifically, this is in the Large Magellanic Cloud, which is our closest neighbor galaxy, about 50 kiloparsecs or 150 light years away. So the target galaxies that we'll be observing with Webb will be about 15 to 30 times farther. So just to keep in mind that, this is not exactly apples to apples, but yet this is a demonstration of how the technique works. So on the left here is a WIFC3 Hubble image of a field in the Large Magellanic Cloud. It's about 100 parsecs across. And in the middle here is the corresponding map of dust that we produced from modeling each individual star in this image. And you can see that the level of detail in this dust map is much higher than what you would get, say, with Herschel, which is shown on the right here. And so not only can we actually do this, but we can do this at a very high resolution. We can map the dust with Hubble. Now we'll have maps of the power properties with Webb and of the interstellar dust with Hubble. And we will therefore be able to derive the abundance of those power molecules. And our ultimate goal is really to understand the mechanisms that are responsible for the formation, the destruction, and the evolution of those power molecules in low metallicity galaxies. And so once we have the maps of those properties, we will be correlating them with different tracers of the interstellar medium and star formation rate in those galaxies. So in this image, you can see the cold atomic gas in red and the coal dust in green. So we'll be correlating the power properties with each of those images to try to understand the role that coal gas and dust play in the formation, destruction, and evolution of PAHs. Similarly, we know where the carbon-producing stellar sources are from previous surveys with Spitzer. And so we will be looking at the distance of those carbon sources to the region that is bright in power emission and to those power properties to try to understand the role that those carbon-producing stellar sources play in the formation of those molecules. And third, we know where the young massive stars are from previous near-UV imaging and spectroscopy. Those are shown in blue in the right image here. And so we can infer the shape and the hardness of the radiation field that bathes those galaxies. And that will allow us to understand the role of this radiation field in the excitation and also the destruction of the PAH molecules. And then finally, we have another Hubble program in those galaxies that has been taking spectroscopy with the cosmic origin spectrograph. And from that, we know the abundances of heavy elements in the gas. So, for example, silicon, iron, and sulfur, etc. And so we can understand something about the chemical evolution of those galaxies. And that will just help us put the properties of the PAHs that we observe with the James Webb Space Telescope into context to try to understand not only the formation, destruction, and evolution mechanisms for PAHs, but also how this is influenced and influences the chemical evolution of these galaxies. And I thank you, and we'll take any questions.
Thank you, Julia, for an excellent talk. I see that we've got a time for maybe one question, which is in the chat, helpfully provided by Bill Blair. He says, at high redshift, Z=2, does absence of PAH emission mean that the PAHs have been destroyed, or does it mean that they haven't even formed yet? Or that does that distinction even matter?
I don't think we know, but the goal is to try to answer that question. Learning from the nearby universe, and I think the fact that our observations will be resolved will be important, right? Because we can correlate the PAH properties with other traces of the ISM and stars, right? We'll be able to understand in what kind of environment these PAHs molecules can form. And granted, those low metallicity galaxies are not perfect analogs to the high redshift universe. But in terms of metal content, they are. And so if the knowledge that we gain in a nearby universe applies at high redshift, then I think we will be able to answer that question.
Great. Thanks again, Julia.